All right, so our next and final segment is going to be electricity. So we will not have a test on Friday. Your final will be the last day class, which is Tuesday. So we'll have the final on Tuesday. We will have a couple of quizzes here and there, but they're very low stakes. You could fail a quiz and it doesn't really matter. It's to help you figure out where you're at, kind of a thing. Not the case on Friday. So Friday will be the last test. It will only be the stuff that we're covering this week and Monday of next week. So it's not cumulative. It's this week and next, be math and electricity. But that's going to take us the whole week here. So we want to start in talking a little bit about electricity. And I was thinking, I don't want to hit you with my notes, and so I want to just give you an overview, and then we'll go across the street, and then we'll come back tomorrow, and we'll kind of pick it up. But when we talk about electricity, we're going to talk about certain things, and these things that we want to talk about are volts, amps, resistance, and power. So we can start with volts. Oh, wait a minute. One slide says it all. I mean, I can just show you this slide and I can go sit down now. Let me see. Electricity. I didn't spend a lot of money on this computer, and now it shows.
Did you buy your own computer?
Yeah. I can't load any of this stuff on if I don't buy my own. I know. First things first. Remember, kids, electricity will kill you.
Is that the sticker on your bottle? I wish I could read that. I thought it was like an airplane or something.
No, somebody bought a whole bunch of these and gave them out. So, all right, electricity in one slide. The volt, the amp, and the ohm, which is resistance. So ohm is resistance. A volt is the pressure that pushes. Amp is what is actually moving, and ohm is resistance to that movement. All right, so volt. What do we got? Where did my pen go? Volt. Volt is pressure. Volt's pressure. Let me see. It is pressure. Its symbol is often E for electromotive force. However, it's measured in volts. Measured in volts. And we give it a capital V because it's named after somebody. Pierre Volta. I don't think it's Pierre, but it's like something. Let me see. Alessandro Volta. So we give it the name volts. So it's pressure. It is also known as the difference of potential. P-O-T-E and T-I-A-L, potential. Boy, I butchered. Sorry about that. Difference of potential. Try it again. P-O-T-E-T.
What's that word next to that? E? The symbol E?
Symbol is E for electromotive force. The important things for you is its pressure and it's the difference of potential. Difference of potential means it's the difference between two things. Your car battery has a positive side and a negative side. Well, all batteries do have a positive and a negative. like your car battery, because it's big and it's got a lot of potential. And what you're doing, if you want to measure how much voltage it is you put a voltmeter on the negative side and in the positive side, and the voltmeter will read the potential between the two plates inside of it. Because one plate has a bunch of electrons and the other plate is deficient of electrons, and it's trying to get there. So that's the potential of it. It's the difference between two things. It is not a flow, it is just pressure. Just like if we were to go into the bathroom right now, not all together, that'd be creepy, and we put a gauge on the faucet and we read the gauge, it would say, I don't know, 12 pounds, 12 psi. That's the potential, it's the pressure in the water pipe. And it's the difference between the pressure in the pipe and out here, believe it or not. It's not just pipe, it's the difference between two things, in the pipe and out of the pipe. If we could somehow take the pressure of the bathroom and bring that up to 25 psi, and it was 25 psi inside the pipe, then the difference of potential would be? Zero. There's no potential. It's 25 inside, 25 outside. So it zeroes it out. So we have this potential there. Amps is actually the flow of electrons. Flow of electrons. Flow of electrons. The symbol is I for intensity, which doesn't make a lot of sense. It's measured in amps. So amps is measured in amps and volts is measured in volts. So you gotta love that. Measured in amps. And like I said, it is the flow of electrons. It is actual movement of something. So when we talk about measuring it, we're actually measuring the movement of electrons. Not the difference of potential, but the movement. Just like if we turned on the faucet in the bathroom, we would measure how much water comes out. We would either get a gallon bucket, measure how many gallons per minute, or something like that. So it is with electrons. Amps. Amps is our measurement. There's other measurements like a coulomb, which is 6.28 times 10 to the 18th power number of electrons passing a certain point under certain, like 1 second, 1 amp in 1 second or something like that. Well, I actually wrote it down. 1 amp, yeah, I was right. So what I just said, but that's not important, so I'm not gonna write it. So, but that is, it's a measurement. So we have to measure flow. And I'll write this again and stress it. When we're measuring the difference of potential, we're not measuring flow, we're measuring between one side to another. When we're measuring amps, we're measuring flow, so everything has to go through the meter, otherwise you're not measuring it. So, all right, let's see, flow, yeah, flow, so flow. Then we have resistance, and the symbol is R for resistance. R, which stands for resistance. It is measured in ohms. By the way, amps is capitalized because that was named after, what was that guy's name? Marie Ampere, French. Ohms is measured, resistance is measured in ohms, and that came from George Simon Ohm, or maybe it's Jorge Simon Ohm. So it is also capitalized. So we get the ohms right there. Ohms is restriction. Is restriction to flow. It causes a voltage drop, which will mean something in a little bit. You can also think of it as electrical friction. Electrical friction. And we'll come back around to power later. I think we've got enough right there. So we have volts, amps, and resistance. Those are going to be our big things that we're working with. Well, since I wrote power. Power is just a mathematical formulation where it's volts times amps equals power. It is expressed in watts. So if you have a 100-watt light bulb, you're just actually just multiplying the power, the voltage times the amps that it uses, and that's how you get the wattage on something. And we get more into wattage and stuff like that when we get into electricity class. This is going to be sort of an overview, very basic. But if you can get the basics down in here, once you get into electrical class, you pretty much just cruise through it. It's we just add a little bit on top of this, add some application. It's not a big deal, I don't think. Just like anything, electricity, just like this class, you almost either get an A or you don't pass. It just works out really nice like that. Maybe you don't think that's nice. So anyway, I tell you all that to tell you that what is electricity again?
Volts, amps, resistance, power.
Right, but overall, I mean, what is electricity? The flow of electrons. So, all right, let's talk about these electrons. What are electrons? Well, to talk about electrons, we got to talk about atoms. So let's just take a very quick look at atoms. Atoms. Well, I always say, anybody ever see this one thing? There's that picture, and I can't believe I didn't put it in here. Thought I did. All right, got that picture. But what's that show? I never really watched it. It's got the, I can't remember the guy's name. It's got that one show with the one guy, but it's got the girl. She's really cute, but everybody's a nerd.
Big Bang Theory?
Big Bang Theory. See, I said nerd. He got it. Big Bang Theory. So, all right. So you got the Big Bang Theory. If you ever watch that and you're a huge fan like I am, the transitions have the little, how about Jimmy Neutron? See, I watched Jimmy Neutron. All right, so you got the little neutron, right? He's got the little atom thing that goes around and has a model. All right, so I want to tell you that we're going to talk about the atom, but there's different models of what an atom looks like. So we can start with the very basic two-dimensional model that the FAA uses, and you can thank them for that. So it makes our life really easy. It's 2 dimensions, and that's what we do because that's what the FAA does. Then you can get into, well, like the Big Bang Theory or Jimmy Neutron, where they've got at least a little model where the atoms, it's an atom orbiting around kind of. But that's even cartoonish and not realistic because if we really look at how an atom behaves, they come up with, there's actually probabilities of where these atoms move, and it gets really crazy. But we don't have to get into that. We can go all the way back to the 2-dimensional model. So I tell you that to guess when you say, oh, look, this is how atom works. And they go, where'd you learn that, in kindergarten? Because it's a very basic model, but it's okay because it works for what we need it to, and that's how the FAA tests. So we're going to stick with it, right? Why make it hard if we don't have to? So the atom is considered to be, I think this is a test question or something, that's why I wrote it. The atom is considered to be the most basic building block, of all matter. Now, one time I thought I'd get really cool with this. I'm like, wow, if we're going to talk about matter and atoms, and well, we ought to start off with the periodic table of elements, and then that was just a bad idea. So we don't need to know any of that to be an aircraft mechanic. So I decided to not do that, but we do need to know this stuff. So if we talk about an atom starts out with we'll build a model of an atom. First thing we have is the nucleus. So we'll talk about an atom. We have the nucleus. That is the tasty center of it. So just over here. So here we have the nucleus. That's my nucleus. And inside of my nucleus, we have a couple of things. We have protons and neutrons. So we can go over here with the red one here. We'll go have a proton. I'll give myself 2 protons. And then I'll come over here. Let me see. Do I add a pen? Let me see. Pen. I need green. green, so we'll use that one. Green, and we'll have some, oh, they're going to be fat, I guess. We'll have some of those, some neutrons. Go back to black. So inside the nucleus, we have a nucleus. It is the center of the atom. The center of the atom. And it contains two things: protons and neutrons. That's where Jimmy got his name, Jimmy Neutron. Do you guys know Jimmy Neutron, the cartoon? Okay, so- All right. Protons are positive charged. Now, when they say positive, it's just what they assigned it. I don't think anybody really knows it's positive, negative. Maybe they do by now, because at one point they had everything backwards, and they go, oh, wait a minute, it's not that, it's the opposite of that. And I'll talk about that. So, but it still worked, and even though people didn't know. And then we have neutrons are neutral charged. Thank you for that. Are neutral charged. And most atoms, I'm just going to regret this decision right now. Yes, I fully regret that decision. I do not regret it anymore. Okay. Most atoms have an equal number of protons and neutrons. So if I have 2 protons, I would have 2 neutrons, and I would also have 2 electrons. What did I make, by the way? Somebody knows this. I think it's 1 and 1, and I think if it's 1 and 1, it's helium. I forget what 2 is. It's a gas. Okay. Then we have pen. Thank you. Nucleus. Outside of the nucleus, we have electrons. So electrons orbit the nucleus in these things called shells. And it's just a fancy word for their orbit. So the very two-dimensional model assumes that these electrons, make an electron here, they orbit around much like the moon would orbit around the Earth. Assuming, of course, the Earth is not flat, which it's not. But if you're a flat earther, I don't want to offend you. So they just kind of orbit around like that. Little dots here for the little orbit. So they're those negative. Okay, so they orbit around in shells. Let me see. If the number of electrons, if the number of electrons equals the number of protons, the atom is neutral. Means it's balanced. Because we have protons, which are what charged? Positive, and the electrons are negative charged. And a negative and a positive, unlike charges, attract. And like charges, repel. So if I had 2 protons, they don't like each other a whole lot. They like their space. They're very territorial. So got a proton here, the other proton's going to be way over there if they can help it. Don't like each other. Both positive, they don't get along for some reason. Electrons the same way. Have a negative and a negative. They don't want to be next to each other. They push each other away. In fact, I think somewhere in here I have a thing where if you actually made an electron the size of a pea and you placed them some 100 feet apart, they still have tons of force. It would actually still move cars out of the way to get out of each other's way. There's so much on there. But unlike charges, attract. Just like a magnet. If I had two north ends of a magnet, you can't bring it together, right? Well, you can, it's just they don't want to do it. But if you take it, turn it around, you have a south and a north, they'll lock into each other. So it's the same way. So we have a positive and a negative, we have a proton and an electron, they actually attract each other. But then you have to say, well, then why don't they just suck in and why doesn't the electron stick to that? Well, because electrons have so much energy, they're like a toddler on crack. They just bounce around. And so I don't just, since it's I don't feed my toddler crack, by the way. Boy, there's a lot of statements I can make there. Drop that one. Okay, so they don't. They buzz around, just like a toddler. And because I have a toddler in my house. And so they buzz around, and so that's why they're orbiting around. I guess they're nervous and they don't want to attract. But that positive and the negative, it kind of holds it into its orbit. And the closer it is, the more it wants to hold it into that orbit. And, it's kind of tied into home and it's happy, so it's good like that. If it has an extra electron, like if I had 3 electrons and 2 protons, that's an extra electron. That is a negatively charged ion. Is a negatively charged ion. So if you see the word ion, you know that's just, okay, that's that particular atom, and it has an extra electron, so I call it an atom. So if it's, let me see, an extra proton, which is another way of saying it's deficient of electron. Extra proton is a positive charged ion. So these little, can't believe I didn't write electrons are negative on here. I better write that now. Electrons have a negative charge. Electrons have a negative charge. Should have wrote that first. All right, they are very fast. So electrons move at about, it's hard to calculate it, about the speed of light. What is the speed of light? 186,000 miles per second. That is reasonably accurate. I tested that. I got a student went down that end of the hallway, and I had a stopwatch and had a flashlight, and I yelled at him, turn it on, and I calculated how long it took, and so it worked out. So that was off. They're off by a little bit, but I'll allow it. Okay. So depending on how many electrons there are, and how they are arranged, makes an item either an insulator, no electron flow, or a conductor. I'll just say electron flow. Doesn't have to be good. You can have bad conductors. So you will have electron flow. And what I mean by that is when we talk about atoms, there's the periodic table of element, and it has all the different atoms, and each atom is built differently. And how that atom is built by God, we didn't build them. They're how it's, well, they do now, I guess. How they're built defines what it is on that element. It could be like 2 and 2. I think that was a gas that I drew. I think 1 electron, 1 proton, 1 neutron. I think that's helium. I forget. I didn't write them all down. It's not my specialty. But we look at these electrons, And we can see how they're built. So how they're built. So let's take a look at some conductors, how they're built. So their gold has its actual atom. There's a gold atom. And the way that works is, let me see, gold. Okay, I'm going to start with gold then. Gold has, in the nucleus, it has 79 protons and how many neutrons? 79. So that's 79, if I'm not mistaken, balanced out. Somebody say 78. All right, good. 79. So 79 protons, 79 neutrons. Therefore, how many electrons? 79. All right. So when electrons orbit about, what is it called where they orbit? Shells. Okay. Well, we can't have 79 of these things in the first orbit or first shell. There is a law that is in existence that you can only have so many in each orbit or shell. And that is a formula called 2n squared, where the n is the shell number. The shell number. So if I want to know how many potential electrons I could have in the first shell, I would use the formula 2, 1 squared. So it's 2 times 1 squared. So 1 times 1 squared is 1 times 1, which is 1 times 2 equals, so the first shell can only have 2 electrons. And then the second one would be 2n squared. So 2 times 2 is 4 times 2 is, does everybody see how that formula works?
So that goes all the way up to 79?
Well, we're just going to do a couple here. So 3 squared is 9 times 2 is 18. Okay, so 2 4 squared. So that's 4 times 4 is 16 times 2 is 32. And then we'll do one more. 2 5 squared. So the fifth shell can have as many as, so 5 times 2 is 25. 5 times 5 is, 5 squared is 25 times 5, so it's 50. 50. All right. So the first shell can have how many, Max? 2. The next one can have then 32, then 50. Doesn't have to fill up each one to go to the next, but it tends to sort of work that way. So if I look at gold, which by the way is gold, would you say that's an insulator or a conductor? Just what you know in life. It's a very good conductor. In fact, that's your very expensive critical parts are covered in gold, or I don't think they use gold wiring because that would be crazy, but they put gold on a conductor to help it conduct very, very well. So gold would have, the first shell would have 2. I got to get to 79. So the next one's going to have, it does have 8. The next one can have, and it does. And the next one has, and it does. Now we're down to, I don't know the math on that, how many I got to, but we're getting close to 60. Okay, we're getting close. No, we don't have 60 yet. Oh, 79. Could have 60 yet. So the next one can have as many as 50. It doesn't. It only has 18. But that doesn't even fill it up. If they have one way out there in the 1, 2, 3, 4, 5, 6th orbit. This one little, it is so far from home, it doesn't even remember home anymore. It can't go home and get an ice cream bar like my kids always seem to do with all their friends. So it'll wander over to the neighbor's house and get their food. Well, actually, that's the other kids in my neighborhood coming to my house and get the food. So you got that one way out there wandering around. That's what makes it a nice conductor, because it's got an electron that freely wanders away from home. And electricity is the flow of electrons. So we have this electron out there. What's another good conductor? Copper. And I heard silver, and those are the only ones I know. So we'll stop there. So copper is, let me see, copper, by the way, has 29 electrons, 29. So gold was 79, copper is 29. That is 2, fills up the next one at 8. Then it goes 18, which follows it, then 1. So again, it's only got 1 out there, and they do call it a free electron, 1 out there, but it's only the 4th orbit out, so it's a little more tied to home. And then silver has 47. And when it goes, silver goes 2, 8, 18, 18, 1. So 1, 2, 3, 4. So it's on the 5th. So that's the 5th. This is the 4th. And this was the 6th, I think. 6th. 1, 2, 3, 4, 5. Yeah, 6th. So you can see that gold is the gold standard, and then copper is the cheaper of them, and then silver is kind of in the middle. Not the way I wrote it. But you can see that they all have 1 electron way out there in kind of...
So does it have anything to do with the higher the number of electrons there are, the better of a conductor it can be? Is that,
I'm going to say yes, only because you're so far out in the shells.
then that way it jumps farther?
Yeah, it's easy. It's easier to knock it off the next one. You don't have to have as much force to move it, to overcome the attraction between the electron and the proton. What's that?
Kind of like less friction.
Less friction. I like that. Okay. So let me see. Electrons, let me see, conductor, yep, electrical flow. All right.
Kevin,
Yeah.
why does copper stop at the 4, silver at the 5th, and gold at the 6th? Is that just where you stopped it, or?
The shell. That's the
Shell.
shell. This is how it's built. This is how God built it.
Oh, that's just given.
It's a given.
Gotcha.
When they were able to figure this all stuff out, somebody sat down and goes, well, look at that. There's 2 there, and there's 8 there, and there's 3, or figured it out somehow. But that's what it is. All right, so electrical flow. Electrical flow. Electricity is the movement. Of electrons from one atom to the other, to another. The fundamental principle is attraction and repulsion. Attraction and repulsion. Because, as I said earlier, unlike charges, do what? Attract. So protons attract what? What do they attract? Electrons. And create stability. Like charges do what? Repel. So electrons repel electrons and create current flow. Electrons repel electrons and create current flow. Based upon my life experience, the protons are the male version and the electrons are the female version. Again, my life experience, which is to say that me being the proton, when I go home and I want to sit down in my lazy boy and watch the TV, well, my wife buzzes around and does all the work. So.
How does that work for you?
How does that equate?
How does that work for you?
I'm here, aren't I? Actually, I prefer to be here. Everybody's got a cold at my house. I'm like, yeah, I'm not home. I'll see you guys later. Oh, because I'm over here. All right. So, yes, I did. I'm not going to write this. If 2 electrons the size of a pea were placed 100 feet apart, they would repel with tons of force. I don't know how many tons, but 2 would be enough for me. So electrons repel with a lot of force. What is, C, direction of current flow? Electricity is the flow of electrons. Electricity flows from
From the negative to the positive.
negative to positive. This guy's crazy.
I mean, yeah.
Yeah, but I'm right. What's the matter?
Oh, what's that word right before flow?
Current?
No. At the end. Yeah, that's right. V8, current.
All right. Direction of current flow. Since electricity is the flow of electrons. The flow of electrons that have a negative charge. Let's see, and that means that electrons repel. Electrons are repelled or repel toward. That's maybe a bad way of saying it. They are attracted to. Toward or attracted. I like that better. Attracted to a positive. So electrons repel towards the positive, or they're attracted to the positive, or they're repelled from the negative. That means that electricity flows from negative to positive. And that is called electron flow theory. Now, electron flow theory was not always the theory. They were figured out electricity, were using electricity, were building things that made electricity for a very long time before somebody said, hey, it's not really flowing from positive to negative like they thought. It's going negative to positive. So it really doesn't matter unless you're into some digital electronics which way it's going, because it worked just fine no matter how you thought of it. Well, I will tell you that conventional flow theory states electricity flows from positive to negative. So we started off with this theory, conventional, way back in the day. I want to say it was like, they ended it, I thought I read something that was like in the 50s. Somebody said no, it was like, then I read something else, like the early 1800s. But so who knows? But originally it was thought that electricity flowed from positive to negative. Now the reason why it works for me to think, they figured that out like in the 50s, which, like I said, could possibly be wrong, is that all electrical schematics for aircraft, cars, things like that, if you're trying to figure out how electricity flows, you're far better off going from positive to negative. And when you see a chart, if I had one to explain it, but we'll later, it just makes more sense to go positive to negative when you're troubleshooting, when you're figuring it out, because all the wires are on the positive side. But it actually flows the other way, and you need to know that. The electron flow theory says it goes from negative to positive. And the reason why that is correct is because if we take a battery, and a battery schematically looks like this side right here is the negative, and this side right there is the positive. The long line is the positive, and the short line is the negative. If I were to do this, and we'll make the wire through the magic of notebook here, very, very large wire right there. Suddenly we have a big electron microscope there, we're looking at it. and it comes back around like this, and we know that we have these, some sort of nucleus in there. We'll just put a couple, we have nucleus, we have these, what orbiting? Electrons orbiting around in there. And since electricity is a flow of electrons, why the electrons, we have a positive plate right here. So if we have a positive plate, and over here we have a negative plate, which means that it has, the positive plate is deficient in electrons. To make a battery, you actually strip out electrons, shove them over to the negative side, so the negative plate has way more electrons than it should have, and when you connect the two, they try and equalize. So all of these electrons are over here. We're trying to equalize around to the positive side of the battery. Well, if these are all negative, then what is it going to do when it gets right here to my little drawing? What is it going to do to this negative one? It's going to send it that way. That's going to repel that one that way. That's going to repel that one that way and repel. But over here in my drawing, I have a positive, and this one right here really wants to be at the positive, so it attracts it over there. So that's why electricity flows that way, and it makes the most sense. But schematically, when you look at a schematic, if we had, and I don't want to take the time to draw a lot of them, but let's see, like that. Let's see, we got a switch, goes to a bus bar. That bus bar is going to go, this is the bus bar, US bus bar. You don't have to draw this out, it's fine. I'm just making a point of something. And this is a very, very crude drawing, obviously. No airplane would really look like this. But what I've drawn is we have a battery, and schematically, when you look at a schematic, it doesn't show the negative wire coming around and connecting to anything, because it's not wired that way on an airplane or a car. You take the negative side of the battery, and if you guys, your car, if you look at it, your battery cable is about that long, and it goes from the battery down to a piece of metal on the chassis, and that's it. And then the positive wire is going to run out. In an aircraft, it'll run through solenoids and switches and goes to a bus bar, which is a distribution bar, right? Mine is like right under my knees, right behind me where all the circuit breakers are. And then from there, we'll go out to, actually, I didn't draw it, but we'll have circuit breakers. That's a circuit breaker to another switch. This would actually be a solenoid right here that would look like that with a solenoidy thing. Anyway, it goes out to each component, and of course there's a lot of components. And if I had to troubleshoot this, I would say, well, it goes from negative to positive, and I'd have to go from the negative. This is a ground wire, and literally components on an aircraft, like that's a light bulb. You have one wire going to the light bulb, and then one wire comes out the light bulb and is that long and just goes to the aluminum frame on the aircraft. So electricity is literally in a metal aircraft going from the battery that far, like mine is in my aircraft, goes through a cable that far to the aluminum frame of the aircraft, or the aluminum of the aircraft. Electricity flows the entire piece of aluminum, would come back through the little wire, go to the light bulb, light up the light bulb, and then follow the positive wire back through the switch, back through the circuit breaker, back to the master solenoid, back to the battery. Literally, that's what it is doing. But it's very hard to conceptualize that, especially when you're doing troubleshooting. If I had a break in a wire right here, I would not want to go, okay, it comes out of here, comes around. So then you have to, in a drawing, you got to look all over for the ground. Oh, there's the ground over there, because the drawings have all kinds of wires. And then you kind of follow it through. And it's just so much easier to go, no, it comes off here, goes master solenoid, master switch. Oh, break is right there. So I just tell you that to say it's a lot easier to conceptualize it going conventional theory than it is the other way around. So, all right, let's see. I think that's a good place to start, because I can see you guys are starting to glaze over. It's like, I don't know what you're talking about. So, well, let's end that and go have fun in the lab.